Okay, so this is sprint 9, my final sprint report. We'll start off by showing the terrain splat mapping, which is my original personal project. I don't quite have time to go over all the engine development that I've done, but I've completed the collision system stuff, the terrain system stuff, the math class, and the visualizer. And I've outlined all that in the written report. So as I've shown in class, the splat mapping works correctly. And this was my initial personal project, and I got it done pretty quickly. So then I moved on to creating the system to more easily write custom shaders for that. Oh, let's go over what that is. Hold on. So that entailed getting the splat mapping working entailed writing the vertex and fragment shaders, choosing what algorithm to use, and then implementing that algorithm. This gets the color from the splat map for each channel, multiplies that times the source texture, adds all those colors up. That algorithm has some problems, but it's also very simple to implement. So that's the algorithm I chose. Storing relevant data, compiling the shader correctly and storing that value, passing in parameters to OpenGL so that the shader gets the right data in from the data that the user passed in. And then a deconstructor for some lists. So that's how that went, and this went pretty quickly for me. So then I decided, oh, it'd be nice. And originally I just hacked it in and just added all the classes all over in the engine. And it wasn't this nice one class. And then I was like, oh, it'd be nice if there was a way to just write one class. So then I wrote the graphics object custom shader class to use as a base class for users to write their own custom shaders. It uses features like the curiously recurring template pattern. It originally it extends graphics object, and that was so that originally I could just plug it into the normal drawing system. It had some variable template argument stuff, so that you could call this create function, and then that would pass stuff to the subclass constructor, but also manage the memory correctly. And then all these functions to wrap up calls to OpenGL. If these weren't wrapped up, you would basically have to copy paste these lines every time you wanted to pass a matrix, pass a int. And then the common draw. This is just the draw for almost every 3D shape. Drawing wireframes is slightly different, but everything else that's solid is just like this. So it can be overridden, but if you don't need to, you don't have to. So I wrote that system, and that worked rather well. And from that, I was able to write a checkerboard shader. I think the fancy shader is like a flashing light. A gradient shader that's in space, like vertically, goes between two colors. The splat map shader I migrated over to this system, and then a UV shader that, based off of the UV coordinates, adds up two colors. So and these are all pretty simple, like an hour or two to write. So it's very quick, much faster than the initial time that I took to write the splat map shader. So that was all well and good, and then I showed that off in class, and then you mentioned that I could do something to speed up the rendering. Let's see if I can pull up my diagram. Where is it? speed up the rendering by rendering the same things at the same time. So I wrote a system to take care of that, heavily based off of the organization of the collision system, but with a bit more, like one more layer to it. Okay, so the overview is the scene owns a custom shader manager, and then every draw frame, draw all is called on that. There should be associations between shader groups in here and then object groups in here. They don't show up because I made a custom list class and I couldn't figure out how to get it to show up in the diagram. So this has a list of custom shader groups, and this has a list of custom shader object groups or bases. So when the custom shader manager calls draw all, it goes through each custom shader group and calls draw all on that. And so every shader is drawn all at the same time. So all the checkerboards are drawn, and then all the gradients are drawn. And within each shader, it's sorted by object. So within a shader, if there's checkerboard cottages and checkerboard spaceships, it would draw all the cottages and then all the spaceships. So this calls draw all, or the draw all, and this calls draw all on the shader object groups. And then shader object groups have a list of graphics objects that all have to be this custom shader class. Oh, and here's all the shaders that I wrote again. And the point of all this was to try to get things to render the same thing all in a row, and then pull out some OpenGL code. I didn't have enough time to properly pull out the OpenGL code. I was aiming towards pulling out the parameter passing, but I didn't get that. The one thing I was able to pull out though, some shader group, I think. Here, so when a shader starts drawing, so this would be all the checkerboard objects in the entire thing, it does use program on the shader type, and use program is an OpenGL call. It's up here, a GL use program, so that sets what current shader is being used. So I was able to pull that out, and that's pretty much the only one I was able to pull out. But on the other hand, just sorting things by object seemed to improve rendering a lot. And I have some data for that. If I look at this one and this one, I ran some quick profiling, and we'll take a look here really quickly. And this guy. Oh, let me show you the scene that this is on. So I did a benchmark when I started rendering, or the rendering, trying to make the rendering pipeline more efficient. I made a new scene, and the scene makes a bunch of static objects. So 500 cottages and 500 gizmos, and that it just renders all those. And we'll take a look at that. So it looks pretty ugly, but doing that. And then I did a quick FPS calculation as well, so I could see how that's going. So I ran profiling on that. And the profiling from before I started working on the rendering pipeline, making it more efficient, Here we go. Draw scene took 87% of the time. After I worked on making the rendering pipeline more efficient, draw scene took 75% of the time. So a bit of speed up, nothing incredible, but a bit. So I thought that was a pretty good result. So my general outline was I made the splat map, then I made the custom shader, then I worked on the pipeline. Oh, let's take a look at some of these classes for the more efficient pipeline, just so you can get a taste of what these are like. So very similar to the collision groups. So it's templated to the shader type, but they're singletons. The other interesting thing I was able to do with this was I was able to get rid of the calls to initialize in the initialize content. So it used to be that the user had to call initialize on all their custom shaders, but since I know that to use their shader they have to register it, and the first time a shader is registered it has to create the shader group. Then in the constructor of the shader group I can initialize it and then verify that it got compiled correctly, and that automated some nice stuff so the user doesn't have to do it, which is nice. So it's templated to the type, to singleton. It registers, it doesn't allow for duplicates, and then it passes it down to a lower level. So let's see, and just regular adding to the stuff, and then draw all, call say use program, and then draw all and all the object groups. And let's look at the object group. It'll be very similar. So it's very similar, but it's double templated so that it maintains that sorting of the shader bucket and then the smaller object bucket within it. So it's singleton with the templating, registering stuff, and then draw all just calls this custom render. And custom render is the same as normal render, but it doesn't custom render doesn't call GLU's program because it was already called by the shader group. I think that's everything I want to go over. Everything else should be in the written report.